R injective,
okay.
and where defined. Implies R bar injective and where defined. The advantage is you have a better handwriting than I do.
Oh, really?
Yeah, your handwriting's pretty nice, Mark.
Oh, really? I guess so. Maybe it's because I'm on the board.
Okay, so so that's conjecture, right? Or claim. Put claim in front. And now put proof. So let's take x, y. No, maybe make it yx. Comma y x prime in R bar implies x y that implies x is equal to y, right?
Wait, x equals x prime, right?
X, yeah. That's what I meant to say. And under the implies sign, or above it, you can write R is injective, or R injective. Right?
R is injective?
No.
No, okay.
Right? If you have x, y, and x prime y in R, because R is injective, it implies that x is x prime, right?
Okay.
So this implies R bar well defined, right? That's the first half, right? I mean, you could say quarter, but half. Now let's take the other situation, right? Y, comma x, and y prime, comma x in R implies
By R is
R well defined, right? So this implies, oh, so y is y prime, and that means that R, no R, oh sorry, R prime,
R prime
is
is injective.
injective. So this is probably the cleanest way to write the proof, right?
Yep. And you have to write it backwards for the. Oh, I see what you do. Okay.
You can say that R double bar is R.
Mm.
So if R, the situation from R goes to R bar, then it goes from R bar to R double bar, but R double bar is R, right? So without compromising your style, you can say the converse follows similarly. Okay.
Okay.
So that's maybe the problem from the exam I cared most about.
Oh, okay.
But does anyone have more questions on the exam?
Can we do the proof for 6?
What was 6?
Explain, show that the union of 3 countable sets is countable.
Oh. So let's call the sets A, B, and C. Okay. And you say that A is countable, so the elements are enumerated. So you have A1, A2, A is like A1, A2, A3, A4, and so on, right? Then B is
B1.
enumerated, so it's B1, B2, B3, and so on. Same for C. And then you would like to enumerate the elements in the union. So you say A1, B1, C1, A2, B2, C2, A3, B3, C3, and so on. This will enumerate the elements of A union B union C, right? And if one of the sets is finite, then we continue this process until we hit the last element, and thereafter we skip that set. So maybe you should put in the precaution what happens if one of the sets is finite. This process would go on and on if all of the sets are infinite. If you never run out of elements to take next. There's somewhere in your homework you had that exercise that the union of 2 innumerable sets is innumerable.
I just remember the real number ones, right?
Real numbers are not innumerable.
Yeah, I know, but that was the only thing I think from that homework where we did something.
Well,
with,
wasn't there one where you had to?
It's irrational.
yeah,
Yeah, I think that's the only one I remember.
yeah.
I thought maybe one of the, I mean, at least in the book there was the problem that the union of innumerable set is innumerable. And we said the cardinality is a little difficult. I mean, if you take the union of 2 sets, you will get the cardinality of the bigger one. They don't simply add. I mean, for finite sets they would add. But the cardinality of the natural numbers plus the cardinality of the natural numbers plus the cardinality of the natural numbers. Right? So this was just a continuation, and we did it with 3 instead of 2. So I was just trying to see whether that had sunk in.
That's the one that
Or I
uses the bar.
wanted to give an easy problem where I thought you have no trouble and it's still relevant. Okay, next question. Maybe some of you need to work through the exam and ask the questions afterwards. So do you know what this is the beginning of?
What this is the beginning of?
Yes.
No.
Think of the most abstract thing. Life.
So you would like to show that given any two sets, there is an injective map one way.
Is that for cardinality?
Yeah.
There's the bijection, right? That requires if there's
No,
the
inject.
same cardinality. Yeah, but injective,
One way.
yeah,
So that means two cardinalities are always comparable.
sure.
What means sure? Prove it.
No, but isn't that in the reading? And then if it's bijective, they have the same cardinality.
Right. But if I give you just two sets,
Uh-huh.
how are you going to compare them?
And go element by element? I don't know.
Transfinite induction. But induction won't work because for finite sets you can do it, but not infinite, right?
I wish I thought like you. You just look up and you look so sophisticated when you're thinking.
Oh, really?
Yeah. I look at my feet.
Look at my nails.
Okay, so we want to prove that given any two cardinalities are comparable. Okay, so if you think about the grand scheme, for cardinality we wanted that they form a linear order. Which means we had to show anti-symmetry, and that was called Cantor-Schroeder-Bernstein.
Sorry, what's that?
Cantor-Schroeder-Bernstein.
Was that the last section?
If they're less than or equal to both
If you
ways.
have an injective map each way,
Then they're equal.
then they are equal. Then there's a bijection. So that means if one cardinality is smaller or equal to the other, and vice versa, then the cardinalities are the same. But to begin with, we must be able to compare cardinalities. Okay, so if I give you two sets, you have to be able to construct a map from one to the other, an injective map. Okay. So let's, you want to, yeah, you can go and write. Take sets A and B. Let A and B be sets, right? Okay. Go ahead.
You don't mind being recorded, yeah?
Just blur it.
Huh?
Just blur out the face.
No, I'll just stop the camera, that's all. I just take a picture of the chalk. It's for Tash, that's why.
So E of A cross B, power set of A cross B, right? No. A in parentheses A cross. So that gives you all of the relations from A to B, right? And in there, maybe we would like to look at the subset. So let's call it C0. Now let's say, so contains P0 equals to. Contains, right? Contains. No, it's a subset. P0, which is equal to the set of R in the set, open set, open
Curly brace, that is open.
Curly brace.
Curly brace.
R in P of A equals P, element P of A equals P. So that R is injective and well defined. And you remember that P of A cross B is partially ordered, right? Any power set is partially ordered by containment, right? Right. So P of A cross B is partially ordered.
That means you count from the empty set. Empty set.
Right, empty set is the smallest and the whole set is the biggest. It is partially ordered. And so is P0, right? Every subset of a partially ordered set is partially ordered, right?
Yeah, what is P-map? Oh, okay.
Maybe let's be careful there. Maybe we should. And I'm saying this because I mean, with the anti-symmetry and or irreflexibility, so when we just go to subsets, no, that's still fine. The only thing is, if we had a diagonal element to begin with, it has to stay there. But that's okay for our P0.
So I forgot the claim. What was the claim again?
No, I was worried about the subtlety that we may encounter as we write things out. So, but that set is partially ordered, right?
So where are we going with this?
We would like to construct a map from A to B or from B to A that is 1 to 1. Yeah, 1 to 1. Now the kind of big claim along the way is R is maximal in P0 You can write claim. R is maximal in P0. If R is the graph of an injective function, from A to B, or R bar is the graph of an injective function from B to A.
Sorry, was that?
What's that thing?
Just let him finish.
How far is,
Oh, sorry.
Hey,
I'll
hey,
let
guys.
us think about
oh, okay.
it.
From B to A.
Actually, it would be the graph of an injective function. Not a graph, the graph. And above also. Yeah. So, I mean, for general orientation and answering the question, this is what we did with order rings, right? That we can pose, if the partial order was maximal, then it was a linear order, right? And you had trouble with that. So that's the equivalent statement here. And then we will complete the proof by applying to Zorn's lemma, right? So this is the key step. Then we throw Zorn's lemma at it and you'll be done.
Which is the key step? That?
No, the claim that we have.
Okay.
On the right, we didn't do anything.
Would you have even gotten that far? Would you have even gotten that far? That's exactly my point.
First,
Let me show that.
No, just commentary.
so let's do one of the easier things.
Okay.
Suppose, so we have three cases on this to deal with. Suppose R is the graph of an injective function from A to B. Does anyone see why it would be maximal?
What does it mean to be maximal? I forgot the definition of maximal.
You can't find anything
It's a
about
maximal.
Is it because if it's injective like that, it goes back to the what we were talking about earlier with the cardinality and then the containment, like all of the stuff, like if that's the one, then all the other ones could be like contained in that one, making that one the maximal one, making that R that particular one.
Well, yeah, so suppose R is a graph of, and suppose R is not maximal. We'll do proof by contradiction, okay? And R is not maximal. So, say R tilde is bigger. Okay. So what does it mean to be bigger?
Is it in
Higher cardinality, more elements?
No. One element. So they exist some AB. In R tilde, and AB is not in R, right? But R was already the graph of the function. Okay. So there must be AB prime in R, right?
Must be prime wire.
Because R is the graph of the function.
So there has to be.
There is
for
some
A.
A comma B prime in R.
And that's because R is
Graph of the
everywhere
function
defined.
is everywhere defined. Okay. So we have AB and AB prime belong to R tilde, right? AB, we have AB and AB prime. In R tilde, and B is not B prime, right?
And this has to be injected, right? So
It has to be well defined.
Okay.
We have this where B is not equal to B prime.
Wouldn't B equal B prime though, because it's contained in R tilde?
That's the
This contradiction part?
Right. And if you want to put the contradiction symbol there,
Is that the lightning bolt?
lightning bolt. We didn't have to write another line. And to be very careful, go 4 lines back. Suppose R is not maximal. That is, R is less than R tilde. No, go back to the board.
The fourth line,
Down.
down one. There you
And
go.
all the way to the right.
No, that's fine. And R tilde is element of P0.
Mm.
Comma?
No,
Oh.
put an element.
Okay, you're just going straight into it.
Element P0. Okay, when we talked about maximal, it was maximal in P0, not in P of A plus B. This is just to remind you so that you really have, there is written that R tilde is in P0. So P0 was things that were injected and were defined. And you get a contradiction to being well defined. So you can pin it down cleanly. Okay. So the last statement where you have R tilde is, well, it's a contradiction to the fact that R tilde is well defined. What you would get down there is R tilde is not in P0, right? Okay, so if R is the graph of a function from A to B, then it's maximal, right?
Yes.
Step 2, if R bar is the graph of an injected function from B to A, then R bar is maximal, right? And by the way, if R is maximal, then R bar is maximal, right?
Sorry, are we trying to show that R is maximal, right?
Right, but we had, it's maximal if R is the graph of an injected function or if R bar is the graph of an injected function. So our first case was if R is the graph of an injected function, it's maximal. If R bar is the graph of an injected function, then R bar is maximal, right?
Oh, because it's an or statement, so you got to show both.
Right. And maybe we should say that R is maximal if and only if R bar is maximal.
Okay, alright.
But if you could make one bigger, you can also make the transpose bigger. Okay, so that means we prove one direction, right? So if we have a graph, it's maximal. So far, so good. Okay, so maybe we want to show the second part. If it's maximal, it's a graph. One way. That if should have two F's, right? In your claim.
If then only one before the R.
If you hadn't gotten that, this is certainly what we want, right? Okay, volunteer. Wherever we are.
Come on, Kyle.
I hope we have.
All right.
Okay, raise the way there. Yeah.
Hey, right on the top board, I always write like.
Okay, so we would like to show maximum implies,
Sister, you gotta get up higher than that.
Do I get a chair or something?
maximum implies graph.
Kyle, go bend down over there so she can stand on your back. Does the arrow go both ways or just one way?
I don't know how to start it.
Yeah, I don't know this art.
Suppose R is not maximal?
Are we contradicting?
I don't know.
Yeah, this is a contrapositive.
Oh, contrapositive.
Interesting. My eyes are terrible. Let's see.
I'm also terrible at writing on the board.
You're doing fine. So if it's not a graph, implies it's not maximal.
So R is not the graph of a function. Injective, well-defined, injective function.
What?
Okay. So R, not graph of a function from A to B. And R bar we'll go to the next one here. R bar is not graph of a function from B to A.
So does that mean that it's still a relation, but it's just not well defined and if we're defined?
No, it's injective and it's well defined. It's a relation, it's injective and well defined.
But it's not everywhere defined, right?
And both R and R bar are injective and well defined. Right?
Are they if they're not the graph of the function?
But it's not the graph of a function, so it's not everywhere defined.
Yeah.
What's missing is being everywhere defined.
So we could choose one to leave out?
No.
No, neither works, right? R is not the graph of a
Okay.
function. Because the claim was there it is either the graph of a function from A to B or B to A. If it's neither, then it's not the R is not the graph of a function from A to B, and R bar is not the graph of a function from B to A, right? Because you had an or in that statement. So if you negate an and, if you negate an or,
Turns into
you
an
get
I guess not.
neither is correct, right? So, what does that mean? R is not graph of a function from A to B.
It means there's not a B for every A, right?
There exists an A. So that
Is it a capital A or a little a?
little a in capital A.
Member A.
And AB, A comma B, is not in capital R for all B, right?
Member B.
What?
All B and member.
Member B. Member capital B.
Actually, let me phrase it a little bit differently. There exists an A sub 0 and A comma, A sub 0 B. Okay. Now let's do the second one. There exists a B0 in capital B. And AB0. Yeah. No, sorry, I should write this differently.
Is it B0, comma A?
Yeah, B0, comma A. Does not belong to A bar, right?
R bar.
R bar. For all A in in summary, A0, B0 does not belong to R. And B0, A0 does not belong to R.
So there's a bigger R or something like that?
Right. So if you take R,
I see.
That's where he's going with it. Yeah?
A0, B0
Mm.
is still injected and well defined. Right?
Sorry, what? One more time?
A0, capital R, union, the element A0, B0, but put curly braces around it. No, that was fine.
Okay.
You're adding sets, that's why. So curly braces around what you just put parentheses around.
No,
No.
only
Around.
the element.
Yeah.
This
There you
would be
go.
The union with the
Two sets.
right, a set consisting of this one element
Mm.
Okay.
is
Bigger than?
bigger and not equal. With equal sign and yes, okay. And this R union, this element is still injected and well defined, right?
Should you denote it? Like call it G or a different thing?
Yeah,
It's just
sure.
easier to write. Call it D.
Call it S.
Fancy R.
No, make it S. S.
Too many people shouting out things.
I would call it D for the Doberman.
Make it S. It's the next letter and the other.
Okay, so S.
Just put an S to the left and put an equal sign.
Of that R union
Okay,
junk.
I gotcha.
Oh, I see.
Is injected and well defined. Right, if you take your two sentences up there, they exist in A0, and with none of the B's it's in the relation, right? So if you add it, it didn't belong there, but it also keeps it injective. No, it keeps it very defined. Okay, the B, that B0 that you throw in, the A0, B0, there wasn't a different B that went with this A0. And the second part that says it stays ejective because there wasn't another A that went to that B0.
Oh, so it's just that one unique pair or whatever.
Right. So you have exactly one for the first coordinate, exactly one for the second coordinate. So we constructed something bigger that is still injective and very fine. So if neither of the things, neither R nor R bar is a graph, then we can make it bigger.
So power already right there then, right? You've shown that you have a bigger set, so you know you have not maximal anymore, right? And therefore Paul.
Right.
So just lightning bolt?
No, not lightning bolt, square.
Square.
Right.
QED. Quite easily done. It's a
That's
lie.
what it meant.
What happened? You tired today? You make us all work.
No,
I like this pace.
Actually, it's not too bad.
Okay.
This is a good pace.
So, we are at the point where we were in the other proof, right? Do you remember what a chain is?
Ooh.
No.
Is that the linear or like the predecessor chain one, right?
Oh.
No, not predecessor.
But I mean, it's a chain though. That's what kind of what a chain is.
A chain just meant a linearly ordered
Yeah,
set,
there you go. It's got to be linear though, right?
right? Right. So, a chain is a linearly ordered subset of a partially ordered set, right? So consider a chain of relations, each of which is injective and well defined. Kyle, go to the board and write it down.
Oh, you've been summoned. You've been summoned.
Yeah, you can move, erase the very left.
The very left or the very right?
I think we may still need the definition out there.
You have all of this?
Yeah, just
Valerie.
I'm done, sorry.
You can see the YouTube video after.
nobody copies anymore, they just take a picture.
I wonder why we take notes when we just take a picture.
Yeah, when I was an undergraduate, at least we had to copy and write it by hand, but
Or we could just use that.
Yeah, you get some look at this.
No.
so,
I want it polished now, Kyle.
I guess it's because I'm so old, I'm just used to copying.
let you.
But what?
Q equal. Open curly brackets, Ri, capital I, sub I. I belongs in some index set. I,
Is it-
capital I.
Wait, what?
I, capital I, member of capital I. Lowercase I is a member of capital I.
But the capital I doesn't have a subscript, right?
Yeah. Shook.
Be a chain injective and well-defined relations. Relations, right?
S. There you go.
And then you would show that Q has an upper bound.
Show that Q has an upper bound.
Call it capital B in PCO. No, just go on. An upper bound B element
Member of
PCO.
the epsilon.
NCPP.
The epsilon, my man. Member of.
Yeah, member of
There you go.
fancy P sub 0. So we claim that this chain of injective and well-defined relations has an upper bound which is also injective and well-defined.
Okay.
Also injected and well-defined.
Okay, are you ready to write one down? B is equal to what?
What?
B is a member of P0.
No.
But what is B? The obvious thing.
It's an upper bound.
It's a relation, right?
It's that.
Mark,
Huh?
didn't you give us the answer last time?
What? What's that?
Last time when we had a chain, we wanted to have an upper bound, right? How did we get there? When we tried to linearly order partial orders.
How did we come up with that? Did we just add something?
That was the rule of the game. That was like the definition.
What did you take? Do you remember?
The
No.
derivative.
I don't remember.
Okay, then let's ask somebody else. Who remembers?
Predecessors.
If it's ordered, can you just take the last one? I don't know. The
There
order.
is no last one.
But it's the upper bound, right? So I mean, you could just walk
Yeah, but
along
there
the
is
chain.
No upper, no last one.
Oh. Just hang out, Kyle.
Sorry, what was the question again?
Find an upper bound for this chain. I mean, there is only one thing that can work. I mean, among all the constructions that you know, which one works? Which one could you apply?
What do you mean by constructions?
You have sets,
Yeah.
and there aren't so many things that you can do with sets, right? You have subsets, you have supersets, you have intersections, you have unions, you have complements. So which construction could you throw at it?
Subsets.
You want an upper bound.
Would that be the less than equal to?
You want something bigger, right? Big is
You come up with these element or one of all J and A.
Well, it's a power set, so I mean the thing is huge, right? Isn't that like the biggest?
Yeah, but you have those things sitting in there, and they are lined up.
Yeah,
Is a chain, so they are linearly ordered.
sure.
So you want to go to the big end.
The deep end of the pool.
Right.
Is that A cross B?
No, that's too much because that is not going to be injected, right? Because you have all pairs, certainly not injected.
Is it like the power set on the thing with jig? I don't know.
No, not that way.
Is it the diagonal A cross B?
Just go down the list. Union, intersection.
Yeah, you said it already, right?
Huh?
You said it already.
Union?
Oh, union.
Yeah, sure.
Ding, 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 ding.
Just take the union of all the RI, right? ZB equals the union,
Yeah, just right here.
Big U, yeah.
big union,
Oh, right, okay.
Subscript.
I in capital I of the RI, right?
This is to infinity, or,
No,
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 I mean-
no, that's it.
okay.
You wrote I in capital I.
Oh, okay.
That does it. Okay, so you would need, you have to show that this union belongs to P0, right? That this relation, it's a relation, right? B is a relation.
Yeah.
B is a subset of P of A cross B, right?
Yep.
Yes.
As
So
it's a member.
certainly a relation.
Yep.
Okay.
Is it injective?
Yes, because they're, no. Yeah, because all the RIs are rejected.
Mhm. But you have to write the two lines through, right? So let's prove it. Show that B is injective. Suppose A comma B and A prime comma B belong to B. And we want to show that A is A prime, right?
Yep.
This implies AB
Equal.
and A prime B belong to Ri for some I.
For some.
Just write it for some I.
This is for some I. Little I. And let me be careful about this thing. AB might belong to Ri. A prime B may belong to Rj.
Okay.
Right? I mean, it belongs to the union, so it belongs to one of the sets, right?
Okay.
Each of them belongs to one of the sets. With me?
AB is a member of RI.
So let's do this step slowly. Erase the last R.
This part?
So let's say A comma B belongs to Ri and A prime B belongs to Rj
Where I not equal
for
J.
I comma J in I, capital I.
Okay. Do you have to say that I and J are different? Or,
No,
Okay.
they could be different, it could be the same.
okay.
But we have a chain, right?
Yeah.
So either Ri is contained in
In
Rj
RJ
or the other way around, right?
Yeah.
Oh, okay.
So AB, this implies AB and A prime B. No, N.
And
No, not that N.
I'll just write down.
yeah.
A
Oh, you were overthinking that one.
belong to Ri for some I. Okay, so if you compare Ri and Rj, then Ri is now the bigger one, right?
Sure.
So that implies A is A prime, right?
Yep.
Because Ri was injected.
Objective. Yep.
So that means B is injected, right?
So you just write that underneath. So B is injective.
And B is injected. So do you want to do the one with well-defined? Row B is well-defined.
What does well-defined mean? All the B's have an A or something?
Yeah,
Or
that's
Because
The other way, right?
Suppose AB
Yeah.
and AB prime belong to B.
there you go. This implies you're doing pretty much the same thing, right?
Yeah, go ahead, tell them.
No, never mind. I give up.
No, you don't, just there.
B is a member of Ri, and AB prime, member of RJ.
where I and J are on this slide.
Yeah. Pretty much the same statement
And
below, right?
implies that the
AB and AB prime, yeah.
Which implies that B equals B prime.
So B is surjective.
No.
Not surjective, sorry, well defined, yeah.
Okay. So B is injective and well-defined, right?
Yeah.
And B is greater or equal to each of the Ri's, right?
Yep.
Yes.
Because it's the union of the RIs, right?
So B is an upper bound, right?
Sure. Just write that so B is an upper bound. Call it a day.
Okay, so on the right-hand side, you can erase all except the first 3 lines.
This.
No, the right.
What's the book?
I think Kyle has the nicest handwriting.
So does everybody still know where we are headed?
I think we're still trying to say game. You are comparable?
Yes.
Wow.
phrase or thing.
What?
No, no, you don't have to write, you may sit down.
Oh.
So we wanted to show that A and B are comparable, as you said, right? Mark said
Yes.
so. So we want to construct an injective map one way. Okay. So in P0, every chain has an upper bound, right? So what does it tell us?
B0 has an upper bound? No? Or you have a maximal? I don't know.
If every chain has an upper bound, then what do you get? Zorn's lemma.
Zorn's lemma. Whatever that means.
Going to what does it say?
Is that the...
Accident choice, right?
Yeah.
It's equivalent to the axiom of choice.
Something about sets you can say, right? For Zorn's lemma.
I can't.
Suppose it's not in there.
Was that in the textbook?
It's a disgrace that they don't have that in there.
We should follow.
But the statement was, if every chain has an upper bound, then there are maximal elements, right?
There exists, like you're guaranteeing the
There
existence?
exists a maximal element.
Okay.
So every chain in P0 has an upper bound.
So therefore it has maximal.
Zorn's lemma tells us that P0 has maximal elements. And every maximal element is the graph of an injective function, one or the other way, right? That's the claim that's still in the middle, right?
Yeah. Is that what Zorn's lemma says? Like it gives you the graph part and all that stuff?
No, Zorn's lemma says if every chain has an upper bound,
It has a maximal.
then there is a maximal element.
Okay.
And this maximal element, in our case, is going to be the graph of an injective function.
Yeah. Because of our claim, right?
Right. Okay, so in the grand scheme of cardinalities, we did go through the entire program, showing that cardinalities give us a linear order, right? Or are linearly ordered. To get that cardinalities are linearly ordered, we need three things: transitivity,
Comparability?
comparability, and antisymmetry.
Oh, okay.
Schröder-Bernstein is antisymmetry.
Because if you have one and then you have like, because yeah, okay.
This tells you comparability.
As Mark pointed out.
Right?
Okay.
And transitivity was trivial. Composition of injective functions is injective.
Okay.
Okay, so cardinalities are linearly ordered. As you casually said, oh, I mean, I have two sets. One set has more elements than the other, right?
Yeah,
Obviously, one way or the other.
sure.
Which I totally agree with when the number of elements is less than 10. But beyond that, you kind of have to prove. And we did that. Okay?
So what are the next 3 lectures going to have in store for us? Is it from the book or more?
Yeah, we can do from the book, sure. modular arithmetic?
Whatever you want to do.
I like the space.
I'd rather go back to the book.
Oh, you know what I mean? I like the pace of this class today.
Oh, the pace is nice, but I still want to go back to the book.
But you did a tremendous amount of work, right?
What's that?
I mean, it's actually a substantial amount that we did today.
4 pages worth.
Guided by our great leader.
No, I probably really go back to the book and they have some modular arithmetic there at the end.
There's only what, 3 lectures left?
3 lectures.
Review and
Review.
test is last 2, yeah.
And the finals cumulative, well, they can do
No,
anything we
that
cover.
was cute.
So my vote for the final is we're gonna have something with truth tables.
Yeah, lots of truth. An entire test of truth tables.
No, never mind. There'd be like 4 or 5 variables. I give up.
The truth is, if I have to make more than 3 truth tables, the last ones will be difficult. I'll think of something.
Sure you will.
No, I mean, we did a fair amount of modular arithmetic. I mean, there's one aspect that we didn't really do. And maybe I go back to Euclid and prime decomposition and uniqueness of prime factorization.
Is that Euclid for that one? The uniqueness of prime factorization?
Yeah.
Okay.
But possibly that's only one lecture. I'll have to think. Okay, see you Wednesday.
Okay.